Hi everyone, we're going to continue on with polarity. So when we think about polarity, we have to think about dipoles and dipole moments. And in chapter 8, when we were talking about covalent bonds and whether they be nonpolar or polar, we also discussed what was a dipole. And a dipole, like we said, was something that has a partial negative and a partial positive charge. We've created some type of partial charges. Just because a molecule possesses a polar bond does not mean that the molecule on a whole will be polar. So remember that bond polarity is just a measure of how equally the electrons in a bond are shared between two atoms of the bond. And then we could think about that as that difference in electronegativity. And I know that we also, in the last chapter, focused on calculating an actual dipole moment. I don't think that you will... Very rarely do we ever use the calculation of dipole moment because electronegativity values and finding the difference between electronegativity values is usually a very easy and sufficient way for us to know whether or not there will be a dipole or whether a bond will be nonpolar covalent or polar covalent. So as the difference in electronegativity increases, remember the bond polarity will also increase. So if I have a very small electronegativity between 0 and 0.4, it should be nonpolar. 0.5 to 1.7-ish should be polar covalent, and then anything above that should be ionic. Okay, bond dipoles and dipole moments are vector quantities, meaning that they have a magnitude and I have to consider their direction. So we looked here at carbon dioxide. Now, if I look at them just half of carbon dioxide, so I'm looking at one carbon-oxygen double bond. Carbon has an electronegativity of 2.5, oxygen 3.5, so it's definitely a polar covalent bond. There are partial charges that we've created based on this dipole in carbon dioxide. So I have a partial positive here, partial negative here, and I can see that with drawing my dipole represented as an arrow. So the arrow head goes to the partial negative, the plus sign goes toward the partial positive. Now, the other side will have the exact same one, so because these are equal in magnitude but opposite in their direction, the overall molecule will be non-polar, and that's because equal and opposite vectors are going to end up kind of canceling each other out. Water is going to be different. So by adding the individual bond dipoles, we can, again, determine that dipole moment. I have 2.1 and 3.5, 2.1 and 3.5. So you would think that water would be nonpolar, but water is a polar molecule because the two bonds do not directly oppose one another. Because they are at that angle, I can't say that they are going to completely cancel one another out. And plus, if I'm looking at, this is oxygen versus my hydrogens, both of the heads, or the dipoles, what's more partial negative charge, is going to be oxygen in both cases. So ultimately my dipole in both of these is moving toward the oxygen, so the overall dipole moment is going to look like this. So they're not canceling each other out in water. For a molecule consisting of more than two atoms, the dipole moment is going to depend on the polarities of the individual bonds and the geometry of the molecule. So I have to look at, is this bond a polar bond? Is there a dipole? And then I want to think about, now all of those bonds together, what would their vectors look like and would they cancel out? I also need to think about the presence of these non-bonding pairs because sometimes the presence of non-bonding pairs make the molecule immediately a polar molecule. Okay, so let's look at, for example, a bunch of these. I have HCl, so this linear one, my dipole is going to be moving toward the chlorine atom because it's more electronegative, so that will have that molecule is polar, partial negative end being on chlorine. If I look at BF3 down here, I have one dipole directed toward fluorine here, and one up here. So if I took the vector sum of the two here on the bottom, it would be one that was straight down, which would balance out the one that is moving straight up. So then that means that BF3 would be a nonpolar molecule. If I look at CCl4, that's also nonpolar, and that's because all of them are directed in the opposite direction. NH3, ammonia, would be polar because N is going to be my more electronegative element. So all of the dipoles are going to be directed towards N. So I don't have them directed in opposite directions. They're actually all coming in towards the nitrogen. So NH3 will be polar. And then if I looked at CH3Cl, so because Cl has a dipole, my carbon-hydrogen bonds do not. But I do have this one carbon-chlorine bond that does have a dipole, so the overall molecule here would be polar. So what I would like you to do for the polarity of molecules that are listed here, it says predict whether the following molecules are polar or nonpolar. So if you would please, for me, just tell me whether they would be polar or nonpolar. We can talk about them tomorrow at the beginning of class. I also want you to look at that worksheet 1 through 6 that you got today, and I want you to fill in whether they would be polar or nonpolar for me, and then we'll talk about those as well at the beginning of class tomorrow. Okay, moving on into hybridization, which we need to talk about atomic overlapping and atomic orbitals, where those are going to be different from when we talk a little bit later in the chapter about molecular orbitals. So valence bond theory, which really is how we get our VSEPR, the molecular geometries and the shapes. Valence bond theory is where we think about bonding electron pairs are concentrated in the regions between atoms and non-bonding electron pairs that lie in directed regions of space. So ultimately, valence bond theory is just really thinking about electrons that are being bonded versus electrons that are being non-bonded and what's happening in the space that's around these electron pairs. That's the valence bond theory, just kind of in a nutshell. So VSEPR model, our molecular geometries, provides a simple way for predicting molecular shape, but it doesn't necessarily explain to us why bonds exist between atoms. It tells us how I could find the shape of a molecule or what it may look like, but it doesn't tell me why they exist. So valence bond theory is trying to tell me why they exist. This is not the perfect theory in the world. There's some really big problems with it, and we just figured out some of these really big problems very recently. So whether or not SP, SP2, and SP3 even happen, we don't know. That could be wrong too, but for right now it works. Okay, how can we use atomic orbitals to explain bonding and to account for molecular geometries? We use valence bond theory because we think about atomic orbitals mixing with one another. So I have an atomic orbital here for 2 hydrogens here. I have an atomic orbital 1s for 1 hydrogen and an atomic orbital 1s for another hydrogen. When they bond, I have a mixing here in the middle when they overlap. So I want to think just about that overlap. What's happening there and why does it happen? That's my goal. So covalent bonds, we know share electrons because the sharing concentrates electron density between the nuclei. So if I'm looking here, my 2 nuclei for hydrogen, that electron density is going to be most prevalent here where that covalent bond is, where there's that overlap. In our valence bond theory, we visualize the buildup of electron density between the 2 nuclei occurring when a valence atomic orbital of 1 atom shares space or overlaps with another atom. So here's my valence bond theory here. The overlap of these orbitals is going to allow the 2 electrons of opposite spin to share space between those 2 nuclei, and that's what forms the covalent bond. So it's this overlap of 2 oppositely charged or 2 oppositely spun electrons, and they're sharing this space, and that's the covalent bond. As the orbitals overlap the electrons in the overlapping region, they are simultaneously attracted to both nuclei. So this hydrogen may have given that electron, but because it's overlapped now, the electron that came from this first hydrogen is going to be attracted by the nuclei over here. Same thing goes for the electron given by this 1s orbital to the nuclei over here. But they are also going to experience some type of repulsion. So we think of covalent bonds formed through sharing of electrons, and it's because of these overlaps. So let's go a little more in depth now. If we think about how the covalent bond should actually look, how much distance should separate the two nuclei, and then how much of the overlap should we actually have in a covalent bond, in those atomic orbitals? It all depends. It depends on what what atoms are overlapping in their atomic orbitals. It depends on electron-electron repulsion, and it depends on the attraction between those electrons and the nucleus. So this graph is trying to show this. Okay, so let's talk about the graph. It says the graph, the graph shows that as the atoms are infinitely apart, so I'm right here right now, as I give tons and tons and tons of space between these two atoms, they're not really going to have that attraction. So I think we could say, like, they're not going to feel each other. I'm not going to have that overlap or the desire for that overlap to happen. So because of that, energy is really at a standstill. It's just a zero. Because ultimately, they're not connected, they're not attracted, so it's really like giving me no energy at all. Okay? As distance decreases, so I'm moving this way, I'm decreasing distance between these two 1s orbitals. I now have a little bit of overlap here. Because I have a little bit of that overlap, I have increased electron density between the two nuclei, so I'm forming my covalent bond now. When that happens, the potential energy of that system is going to decrease. So energy is going to be here in my negative. I'm forming an attraction. Okay? So potential energy decreases with increasing atomic orbital overlap. Let's say that I increase it even more. Now I'm going to have a balance between the attraction of the electrons in the covalent bond with the nuclei versus the repulsion of the electrons and the repulsion of the nuclei. But guess what? I can overlap way too much. And if I start to overlap way too much, then I'm going to get way too much nucleus-nucleus repulsion. So if I have too much nucleus repulsion, then what's going to happen to the amount of my energy? Ultimately, it's going to start to approach zero again, meaning that I don't like that. Will you please let cakes in? Thank you. Meaning that I don't want that energy here to be zero. So if I don't have enough overlap, then I'm not going to get a good, strong covalent bond. But if I have too much overlap, I have nucleus repulsion or nuclei repulsion. So there is a balance between repulsive and attractive forces, and that's what this graph is trying to show us. So increased overlap brings electron and nuclei closer together while trying to decrease electron-electron repulsion. But if I get too close, nuclei are going to repel, and that's going to raise the energy greatly. And I want to try to have that balance of potential energy here. Okay. Let's talk about hybrid orbitals now. And let's just, for a second, we're going to think about beryllium and with fluorine, but how can we reconcile the notion that covalent bonds are formed from overlap of atomic orbitals with molecular geometries that come from this VSEPR theory? Okay, so we assume that atomic orbitals can mix to make new orbitals, and those new orbitals are something that we call a hybrid orbital. The shapes of hybrid orbitals are different from the shapes of the original orbitals, and that's okay. It's just we're going to predict not only domain geometry, not only molecular geometry, but now we also have to include this hybridization. So the process of mixing these atomic orbitals, we said, is hybridization. The total number of atomic orbitals should remain constant for the atom. So number of hybrid orbitals equals the number of atomic orbitals that are mixed, okay? So if I have one atomic orbital, I should see one hybrid orbital there. Okay, so for example, let's look at beryllium. Beryllium in its ground state electron configuration or orbital diagram here would show me 1s, 2s. So it'd be 1s2, 2s2. So 1s2, 2s2. We would think that beryllium wouldn't be able to form a bond, and we would think that it wouldn't be able to form a bond because it doesn't have any unoccupied electrons. But we know better than that. We know that beryllium is found in nature, bonded to other things. So how is it possible? It is possible because if one of the electrons absorbs a small amount of energy, beryllium can become excited, meaning that one of the electrons in the 2s orbital is now going to move up to the 2p orbital. So now it can form up to 2 bonds because there are 2 there are 2 unpaired electrons, one in the 2s and then one in the 2p. Okay? But there's a problem here, and that's because, are these bonds going to be the same? If I bond, let's just say we're going to bond fluorine to the 2p, and then another fluorine atom to the 2s. Those bonds are not going to be identical. And when we look at beryllium fluoride in nature, we actually find that the bond lengths of both of them are equal. So if this doesn't work, what do I do now? Now we get to something called hybridization. So what really happens is that the 2s orbital and the 2p orbital are going to mix to make something called the sp orbital. So I'm going to have one s orbital and one p orbital, so I have 2 atomic orbitals total, mixing to make 2 sp hybrid orbitals. And if I have them both together, I can see the sp hybrid orbitals are here shown together. Okay, mixing s and p yields 2 degenerate orbitals, meaning, so degenerate meaning even energy level, yes? So degenerate orbitals that are hybrids of the 2 orbitals. So an s and a p come together to make an sp hybrid orbital. So if I'm thinking about this in terms of beryllium fluoride, so S and P making this, let's look at this. So this is the overall sp hybrid orbital. Here's beryllium. This is the sp hybrid orbital. That one unoccupied, or that one unpaired electron here for fluorine comes and shares here. The one unpaired for fluorine comes and shares here. So this overlap region here is what's forming that bond. This is consistent with the molecular geometry that we see with Vesper. So they align themselves to minimize as much repulsion as they can, which would be 180 degrees. If we drew the Lewis structure for beryllium fluoride, if we used Vesper to predict electron domain and molecular geometry, we would say that it is linear. And that linear geometry totally corresponds with what we find for its hybridization. So I would say that BF2 has a hybridization of sp because it's using sp orbitals, okay? So if I wanted to draw the orbital diagram for this in terms of beryllium's hybrid orbital, I have one s, and then we used to have that 2s, and I used to have one that was in the 2p, because remember we had it excited. Let's go back. So I was here, but I mixed these two. I mixed an s and I mixed one of the p's, which is why now I have an sp. So I have my 1s, then sp, and then 2p, okay? So that's what an orbital diagram would look like. So the sp orbital is going to be higher in energy than 1s, but it's going to be a little bit lower in energy than 2p. I can do the exact same thing if I think about boron bonding to maybe fluorine, for example. So in this case, I'm going to end up having a 1s orbital and then 2p orbitals. So because of that, I have 3 atomic orbitals that are about to overlap. So since I have to keep however many atomic orbitals I have is how many hybrid orbitals I'm making. I can make 3 sp2 hybrid orbitals. So if I bring all of them together, it's going to look like this. the sp2 hybrid orbitals that are shown together here, okay? For sp2 hybrid orbitals, since usually we think about them mostly lying in the same plane, they are 120 degrees apart from one another, so that should make us think on which term of molecular geometry should make me think trigonal planar. So anything that's in the electron domain geometry of trigonal planar would have a hybridization of sp2. Anything that's in the linear electron domain would have a hybridization of sp. I can say the same thing in terms of tetrahedral sp3, meaning I'm going to take one s orbital and 3 of the p orbitals, and then I'm going to make, so I have 4 atomic orbitals shown here. I blend them to make 4 hybrid orbitals here, and I bring those 4 hybrid orbitals together to form this overlap hybridization. So sp3 hybridization is going to work for the tetrahedral electron domain geometry. Okay, so hybridization doesn't just have to be, though, for all bonding pairs. I can also use hybridization to describe bonding in molecules that contain non-bonding pairs. It will work the exact same way. So if we're looking at, for example, water, I know that oxygen has 4 electron domains, 2 bonding and then 2 non-bonding. So water would have an sp3 hybridization about the oxygen because it has those 4 electron domains. It's in that tetrahedral electron domain geometry. So non-bonding pairs are also going to count as part of that hybridization, okay? So just a summary, it's sp, its geometry would be linear, and we're really thinking electron domain geometry, okay? sp2 means that I'm taking or mixing one s orbital, a p orbital, and another p orbital. So that's going to give me sp2. So I have 3 then orbitals that I've mixed here. 1, 2, 3. I see those there. That's going to be trigonal planar electron domain geometry. And then if I take 3 p orbitals and mix with an s, that's going to give me sp3. And that's going to be my tetrahedral electron domain geometry. So we can go, at least we thought, we can go past period 3. I could be able to get into the d orbital. We don't. We can't. We thought we did, but we have no idea. So sp3d and sp3d2 are things that will not be tested on your AP test. And that's just because there's so much that's up in the air about them that we can't definitively say whether or not your answer would be right or wrong if you tried to argue something. So only ones we need to know for hybridization are sp, sp2, sp3. Okay, so here's my summary. I'm going to give you a molecule, you're going to draw the Lewis structure, then you're going to tell me electron domain geometry, then you're going to tell me molecular geometry, you're going to tell me bond angle, steric number, if it's polar or nonpolar, you're also going to tell me what its hybridization is, okay? So, valence bond theory, pretty much hybridization is the biggest player in the valence bond theory. But there's also 2 very distinct names that we have given in ways that these atomic orbitals can overlap to form bonds between atoms. I think you've heard of these. These are sigma bonds and these are pi bonds. So a sigma bond is, in the covalent bond, let's go back to just thinking about a covalent bond. In a covalent bond, we've considered electron density aligning between 2 nuclei. So here's my nuclei here, and here's a nuclei here. The overlap is where that covalent bond is formed. When I think about that electron density, I usually think about it in line with the nuclei. So when something is in line with the 2 nuclei, we call that the internuclear axis. A sigma bond is characterized by a head-to-head overlap. And we call it a head-to-head overlap because it's in line with the internuclear axis. So So the line joining the two nuclei is called the internuclear axis, and a sigma bond is when I can have that internuclear axis going straight through that overlap. And I have that here. So my sigma bond would be right here. Head-to-head, overlap, internuclear axis passes straight through. That's different than a pi bond, which we can see here. Pi bonds are going to be characterized by a side-to-side overlap. So unlike the sigma bond, the pi bond electron density is not concentrated on the internuclear axis. So I can have a pi bond that's going to be above that internuclear axis. I'm going to see pi bond here, part of that p orbital that's going to be below that internuclear axis. So there's an overlap because of the sideways over. Pi bonds are going to be a weaker overlap versus a sigma bond. And a pi bond is a weaker overlap because of the sideways overlap just on its own. It makes the pi bond weaker. It's not as strong as being with that internuclear axis versus a pi bond that's going to be around that internuclear axis. Okay, so how can I determine if something has a sigma bond or if something has a pi bond? So single bonds are always sigma bonds, and that's just because I have to have some type of head-to-head overlap for a single bond. There are some exceptions to that, so I maybe shouldn't say that they're always sigma bonds, but for us in AP Chemistry, they are always going to be sigma bonds. Single bonds will. So in almost all cases, sigma bonds are single bonds. A double bond is going to consist of one sigma bond and one pi bond. And then a triple bond is going to consist of a sigma bond and two pi bonds, okay? So in hydrogen, I have a sigma bond here because there's that single bond. If I'm looking at C2H4, that double bond here is going to be one sigma bond, so one of the bonds is represented by a head-to-head overlap, and then one is going to be represented by an overlap below and above the internuclear axis. If I look at my nitrogen molecule, because it's a triple, one represents sigma, so I have that usually an S orbital overlap, and then two pi bonds. Okay, so in a multiple bond, one of the bonds is sigma, and then the rest are going to be pi bonds. Okay, we're going to practice with hybridization and sigma pi bonds tomorrow in class. So we'll also just pick up here, because we're rocking at 27 minutes. Okay, I will see you guys tomorrow, and I hope you have a really wonderful night. Bye.